Okay, so this is going to build on what we did last time when we did integration by substitution. So the only difference is we're going to have definite integrals. So I'm going to give you two options, because options are good. I'll tell you which one I prefer, but it's not very complicated. So the first option is to go back to the original variable. So you substitute, right? You do whatever substitution you want to do. You go back to the original variable, which is basically what we were doing all last time, right? And plug in the values. So this is kind of the more natural way to do it when you're first starting off. But the second way that I'll show you is typically harder at first, but easier going forward, typically. Not all the time. So let's say, for example, you have the integral from 2 to 7 of x e to the x squared, for example. Okay, so we remember what to do, right? We do our substitution. What would be a good substitution here? X squared, good. Okay, so then we find du, right, which is 2x dx. So then we multiply by 2.5, right? Is that okay? All right, so then my 2x dx, that is du. Okay, so now this is where it's a little bit different. So what you do basically is you say, okay, I'm going to look at the integral without limits of integration. So pretend like it's a problem that we did last time, and you just say, okay, well, basically I just have this problem, which is if I do my substitution, I end up with e to the what? E to the u du, right? So I end up with 1/2 the integral of e to the u du, which is then equal to what? 1/2 times e to the u, yep, plus c, which is then equal to 1/2 times e to the x squared plus c, right? Okay. All right, so this is at this point no different than what we did last time, right? So then all you have to do is just put in the limits of integration at that point. So then you say, okay, well then the integral from 2 to 7 of x e to the x squared dx is equal to 1/2 e to the x squared, that's my antiderivative, right? Evaluated from 2 to 7. And so then you just plug them in like you normally would. So 1/2 e to the 7 squared, right? Minus 1/2 e to the 2 squared. And however you want to write that. You can do 49 minus e to the 4, or factor out the 1/2, whatever. But but that strategy probably makes a lot of sense, right? I mean, it's pretty much what we did last time, except you have limits of integration. You just have to make sure. So what you don't want to do is, so this would be something you don't want to do. Okay, so don't write this down. Do not do this. Because notice at this point, what are you saying? If I put that 2 and that 7 right there. What am I saying these represent right here? Those. The limits of integration, what are those? Those represent x values originally, right? If I stick them right there where I put the red arrows, what does that mean? I'm saying u is equal to 2 and u is equal to 7. Is that true?
No.
Nope. because u is x squared, right? So what happens often is students will go like this, and then they'll put a 2 and a 7 here, and then they'll plug in the 2 and the 7 for u, which is not okay, right? Because 2 and 7 are x values. Yes? Okay, all right. So that's good. So any questions about that? No? Okay, so now, just to make sure things aren't completely clear, let's look at option 2. Okay, so option 2 is to change the limits of integration to the equivalent value in the new variable, let's say. Okay, all right, so let's say, for example, we have the integral from 7 pi over 6 to, I don't know what happened there, to 5 pi over 4 of sine x cosine x dx. Okay, so what we do here, so why don't let me first, before I do anything, these guys right here are x values, right? Okay, so I'm going to emphasize that. I'm going to write x equals here and x equals there. Okay, so those are x values. All right, so what would be a good substitution? Yeah, so actually either one is fine. Probably sine x works a little bit better. Because the derivative, what's the derivative of sine x? Well, it's cosine x. What's the derivative of cosine x? Minus sine x. So you can either pick whichever one you want, actually works fine. So let's do u as sine x just to make it a little bit easier. Less signs to worry about. So what would du equal to here? It would be cosine x dx, right? So notice this cosine x dx is du, and sine x is u. So notice that this is going to equal to the integral of u du, right? Okay, so this is the nice thing about changing the limits of integration. So what we do here is we say, okay, well, if x goes from 7 pi over 6 to 5 pi over 4, let's change those to what u equals to, given this substitution that we picked, the u equals to sine of x. So notice when x equals 7 pi over 6, u is going to equal to sine of 7 pi over 6, right? And what's sine of 7 pi over 6? Birds chirping. Negative 1/2, yep. Okay, so where's that going to go? That's going to go right here, where the 7 pi over 6 was. Now, so instead of x equaling 7 pi over 6, we have u equals minus 1/2. Does that make sense? The change? And then the other change is when x equals to, in this case, 5 pi over 4, u is equal to sine of 5 pi over 4, right? Which is what? Negative root 2 over 2, right? So where is that going to go? And that's going to go at the top, minus root 2 over 2, like that. Does that make sense, where those two come from? Okay, so the nice thing about this, though, is that now, so we do the next step, right? Find the antiderivative. What do we get? U squared over 2, right? And then what do? Well, I'm just going to evaluate from minus 1/2 to minus root 2 over 2. So what do we get if we do that? That would be root 2 over 2 squared. What is that? A half. Yep. So, well, I don't know. Yeah, that's fine. We divide a half by, or a half divided by a half is a fourth, right? Okay. And then what else? Minus, if I plug in minus a half, what do I get? 1/4, right? And then divided by 2, I get an eighth. So what is that? 1/8, right? So the nice thing about this is we don't have to go back to our substitution, which was sine of x, right? So instead of going u and then, okay, well now let's go back to what u equals, which is sine x, and then plug 7 pi over 6 and 5 pi over 4. Instead, you just kind of plug them in on the side here, right? And then you can just stick with u to the end. The main thing, so neither of these is very difficult. The main thing you have to be careful is not to mix them up, because often students will, for example, do stuff, funny things like for example, we'll have this. So don't do this. Do not do this. So like 7 pi over 6, 5 pi over 4. Every semester I get students tell me, I would never do that, and then they do it. All right, so you have this, right? So what do we say? Minus a half, minus root 2 over 2, u du. Okay, I see this all the time. Let's see. Okay, so you get this, right? Okay, and then, well, u was sine of x, right? So sine x squared over 2 from minus 1/2 to minus root 2 over 2, which is then sine of minus root 2 over 2 squared over 2. Right, so what do you guys think about this? Exactly. That's the problem, right? That we need to make sure that we keep straight what's what, right? So here, these are u values. These are x values. So they don't mix, right? So, do you guys see the problem? Yeah. Okay, so don't do this. So I'll put a big fat X. Do not do this. All right, so pick either option 1 or option 2. It doesn't matter. I tend to favor option 2 because it involves less going back and forth, but it's up to you. What is it? Option 2. You like option 2 better, huh? Okay. Well, good. All right, you guys want to try one? So one thing you might find helpful to do is to say explicitly what the limits of integration represent. That way you'll always know what it is, right? So here we said we were going to do u is tangent of x, right? Because we recognize that the derivative is secant squared x dx. Okay, so then I'm going to have the integral of square root of u du, right? Okay, and then I'm going to switch the limits of integration to u values. Now, you don't have to write u equals, but especially in the beginning, you might find it helpful because then you keep track of what step you're on, right? So here I made clear that x equals 0 and x equals pi over 4. So I need to change those from x values into u values, right? Does that make sense? Okay, so then I plug them into my substitution, which was tangent, right? So tangent of 0 is 0. Tangent of pi over 4 is 1. So then u is going to go from 0 to 1. Does that make sense? Okay. And then I find the antiderivative, which is, so we add 1, right? So 3/2, and then times the reciprocal, which is 2/3. And then this is evaluated from 0 to 1, right? Because those are u values. And then what do you get? 2/3 times 1 to the 3/2 minus 0. So basically you just end up with 2/3, right? Questions? Yes?
Can you explain why you chose just tan x and not root tan x?
Yes. Good question. The main reason is that if you choose square root of tan x, that it won't work. So here, and that's okay, you know, you can choose the wrong substitution as long as you recognize it and then fix it. So if I let u be square root of tan x, what would du equal to? It would be root tan x times secant squared x dx, right? Okay. So, well, let's see. Yeah, I mean, well, can you make this work? I don't know. Maybe. So notice how you don't really have du here. Let's try for fun. Let's say we solve for dx. What would we get? You would get 2 root tan x du over secant squared x, right? Okay. All right. So it kind of looks like a bit of a mess, but let's just go with it, see where it leads us. And then, so here I'm going to just substitute all this stuff that I just found, dx to be. So I have 2 square root of tan x du over secant squared x. So now what do I get? So secant squared x cancels, right? And then I end up with, oh, I wish I had more room here. Well, okay. So this is equal to the integral of 2 tangent x, right? Du. Okay, well, what's tangent x equal to? So this is actually a very good question. Well, what's tangent x equal to? If u is root tan x, then tan x is u squared, right? So does that substitution work? It actually does. surprisingly, right? So what is this equal to? This is equal to 2u cubed over 3, right? That's the antiderivative just by itself. Would the limits of integration be the same? If I'm going from 0 to pi over 4, these are x values. What would u equal to? So now notice you're plugging it into square root of tan x. So what's square root of tan 0? 0. What's square root of tan pi over 4? Aha. So what do you think? 2/3. Look at that. Wowzers. Wowzers. Okay, so the answer to the question is actually not because it's wrong. The answer to the question is it doesn't matter. You can do either one. So both work. But the second one is a little bit crazier, right? I mean, but it works. So that's fine. Whatever floats your boat. Yeah.
So we don't have to worry about the square root because we can find the derivative of, or the antiderivative of u squared, right? Is that the whole idea? That we don't have to worry about the square root?
Yes.
Okay.
You're right. So for example, when I look at this, the original integral, when I look at that, I immediately notice that I have a function inside of something, right? So here in this case, square root. And then I immediately also notice that its derivative is right there in the integral. I right away gravitate towards let u be the inside, and then I know that I'm not gonna have any issues evaluating the integral. But there are also times when you don't know what to do, and this is a good strategy where you let u be something, a lot of times with a square root actually, and then you find du, solve for dx, and then you just kind of go for it and hope that it works out, which is kind of what we did here. And then we said, wowzers, look at that, it worked, right? But did it look like it was going to work? It did not look like it was going to work. We were lucky a little bit.
If the values that, like the original interval from 0 to pi over 4, if those gave us like not such nice values, would they still have worked?
Yeah, just the limits of integration would have been different. So like for example, so compare, let's just say we change it. So the same thing, right? Tangent x, secant squared x. So let's say you have, for example, pi over 6 to pi over 3, for example. So if I do the first substitution where u is equal to tan x, then what would I get? So when x is pi over 6, u would equal to, what's tangent of pi over 6? So sine of pi over 6 over cosine of pi over 6, which is 1 over root 3. Good. 1 over root 3. And then when x is pi over 3, u is equal to it's good trig practice. Root 3. Yep. Whoa, wowzers. Root 3. Okay. And then you would do whatever, right? So same thing, right? 2/3 u to 3 halves from 1 over root 3 to root 3. And then whatever you get there, right? Stuff. Okay. And what would that look like? So the same exact integral. But then this time, you do u is square root of tangent x. So what would the limits of integration be that time? Well, now it's going to be 1 over the 4th root of 3, right? Because they're going to be the square root of the square root of 3, which is the fourth root, 3, right? And then this one would be the fourth root of 3. But notice the integral is different, right? What would be the integral in this one? What was it? Was it u? Or u? I forgot already. 2u squared. 2u squared is what we ended up with. And when you integrate this, you get 2u cubed over 3, evaluated from 1 over the fourth root of 3 to the fourth root of 3. And are those two the same thing? Those two, if we were to evaluate the top one and the bottom one, do we get exactly the same thing? You better, right? You'd better, and you do. Because notice you plug in root 3 into here. Notice you're raising it to the third, but then you're also getting the square root right there, right? Here, you already have the fourth root, and you're only cubing it. So it ends up being exactly the same thing. So, same. Same, but different. But they both work. Yes?
Can you, on the previous slide, go back and explain how if you use square root of tan x for u, how you got du?
We just got the derivative of it. So the derivative of, we have to use the chain rule, right? So the derivative of square root of tangent x is, yeah. Yeah, I mean, the main problem, the main difference between the two really is that the first one, you're pretty much sure that it's going to work. And then the second one, you're hoping it's going to work. And it turns out it does, but, and sometimes you have to just do that anyways, you know, just hope that it works, because you don't know. But it's always nicer if you know it's going to work, right?
It's not always the case.
What? That you're going to have two very different approaches that are going to work with the same problem?
Like, it's not always going to be the case that u equals tan x or like the function.
Yeah, no.
Side
It's definitely on a, problem by problem basis for sure. Yeah. I would not use this as a rule to apply to other problems. But it is nice when there's more than one solution, you know, more than one way to get to the solution. So, fun times. That was a great problem. Do you guys want to do another one? Sure. Okay, so what did you guys pick for your u? Square root of x. Okay, good. So then du is 1 over 2 root x dx, right? And is that looking promising? It is, right? Because notice I have 1, basically I have 1 over root x dx, so I can just multiply it by 2 on the bottom and 2 on the top, right? So then this right here, dx over 2 root x, that's equal to du, right? And then, so then what is this equal to? This is equal to the integral of sine of root x, which is u, du, right? Does that make sense?
So what about the 2 on the outside?
It still goes there, yeah. Yeah, so the 2 should still be there. Let me, hold on. Let me rewrite this a little bit. So 2 equals, okay. Now, the limits of integration then, what do those change to? So if u is root x, then when x is pi over 2, u is going to be square root of pi squared, which is just pi, right? And what about the top limit of integration? It would be the square root of 4 pi squared, which is 2 pi. Yeah? Okay. And then, let's see. So what does that equal to? That's 2 times the antiderivative of sine of u. What is that? Minus cosine, right? And then this is from u equals pi to u equals 2 pi. So this is minus 2 times cosine of 2 pi minus cosine of pi, which is minus 2 times, what is that? Zero, right? Nope. It's not zero. Gotta be careful. Gotta be careful. Okay, so what's cosine of pi? Minus 1. Alright, so then minus 4, right? Alright, so make sure you guys are careful. Careful, careful. Alright, what about the bottom one? The bottom one's tricky. So there isn't really much that kind of screams out at you. Letting u be the inside in this case doesn't quite work because, well, you can try it, but what do you end up with? You end up with minus 1 dx for du. What would that equal to? So this would be a minus du. You would have a square root of u, and then what's square root of x? That would be the square root of, if you solve for x here, you would get what? 4 minus u, right? So what do you think about that compared to the original one? Looks almost identical, right? So that's no good. Okay, so I mean, you know, that kind of stuff happens more often than we would like, probably. So, okay, well then we start over. One of the things that, so if you're at a loss for what to do, which, I mean, there aren't really many options for this one, right, at this point. I mean, what else can you do? There's no quotient rule or product rule or any weird stuff like that. So one thing that often works, if you have the square root of x, to just let u be square root of x, and then just kind of go through the steps and hope that it emerges as a better integral to evaluate at the end. So let's try that. So typically what you do in this case is you find u, you find du, and then kind of like the weird one that we did earlier, you solve for dx, and then you just kind of plug it all in and then hope that stuff cancels. So that's what we're going to do. Okay, so let's try that. Let's see what happens. So what do I have here? I have 1 dx, so this is going to be, so I'm going to, instead of dx, I'm going to plug in 2 root x du over square root of 4 minus x, right? Okay, now you might have maybe plugged in u here, maybe, I don't know, right? Or maybe you left it as square root of x. Either way, u is equal to square root of x, right? So I'm going to go back to putting a square root of x there because they cancel out, right? The square root of x's. So it doesn't matter if you change it into a u, they would still cancel because u equals square root of x. Okay, but notice this is still a problem, right? Because now you have du over the square root of 4 minus x, not 4 minus u. So now what do you do? Well, you need to figure out some way to turn that x into a u. So then what you do is you go back to the original substitution and you ask yourself, what would Newton do? No, I'm just kidding. No, What is x equal to?
U squared.
X equals to u squared, right? You can solve for x there. So then you go, okay, well, this is equal to 2 times the integral of du over the square root of 4 minus u squared. Now, what do we think about that compared to... So, is that something that we know how to evaluate?
The 4 inside is okay, right?
What does that look like? We've done this before, right? Yeah, it looks like inverse sine, right? So what would we do though? So we did some of these last time. What would be the first thing that you need? That 4 can't be there, right? What does it need to be? It needs to be a 1, right? So what do? You factor it out, right? So you go, okay, well, this is equal to the square root of 4 times the square root of 1 minus u squared over 4, right? Okay. So then so notice, what do I have to do now? I have to do another substitution, right? Don't I? Yeah, because I need this to be, so this is what I need. I need, well, I'm just putting those guys there like that. But basically you need this to be whatever, right? Some other letter. Let's pick W. But we need to have the square root of 1 minus blah squared. So let's just pick W because it's a different letter than U. So how am I going to get there? What's the substitution I need? W equals to what? U over 2, right? So then what would dW equal to? 1/2 du, right? So then du, this du is equal to 2 dW, right? Yes or no? dW is du is equal to 2 dW.
W equals u over 2, not u squared over 2.
Right. Because we want to end up with 1 minus W squared under the radical. Because we're going to then change it into arc sine. Right? So notice here, these 2's cancel, right? So then you end up with, this is 2 arc sine of W, right? Which is fine, I guess. But then what about the limits of integration? We kind of forgot about them, right? So what do you guys want to do? Should we change the x's to w's? Yeah, sure. Either way, whatever you want, whatever floats your boat. I'm more worried about that I don't have enough room to write down stuff here, but let's just put them right here. All right, so what is u equal to? When x equals 1, u is equal to 1. When x equals 2, u is root 2. Okay, good. All right, and then what about, so down here, w. So this is 1 root 2, 1 root 2, right? So when u is 1, w is 1/2. When u is square root of 2, w is root 2 over 2. Right? Okay, so what's that equal to? 2 times, what's the inverse sine of root 2 over 2? Pi over 4, good. Minus inverse sine of 1/2? Pi over 6. Look at that. We fit it in there. So, what is that? 5 or 6? I think. Pi over 2 minus pi over 3. Just pi over 6. All right. Look at that. Nice. Strong work, team. All right. So what do you guys think? Fun times, right? Fun times, indeed. Any questions with that one? No?